Previously, we have discussed that if we knew which component xi from, meaning we are now getting data xi, zi, zi indicates which component xi is from, then the joint likelihood is easy to deal with, and the MLE for all those parameters are in closed form. But of course, the problem is that we do not observe the zi's. This is why we call them latent variables. Now let's consider the following iterative scheme where we start with some initial guess of the parameter theta. So we're going to have some initial guess of the mean and variance of the two normals and also the mixing weight pi. And then we can compute for every xi, we can compute the corresponding distribution of this binary variable zi. We can compute the probability given the value of xi, what is the chance that zi is from the first component. So the calculation is very much the same as the calculation we did in week 1 when we do classification. And similarly, we can compute what is the probability of zi is equal to 2. And then for every observation xi, instead of allocating it to either component, we're going to count gamma I, which is a probability, gamma I fraction of it to component 1, and 1 minus gamma I fraction to component 2. Remember, gamma I is the probability of zi is from component 1. So for example, if for observation x1, the probability of x1 is from the first component is, let's see, 75%. Then we're going to count 75% of the first observation as if it is from component 1, and the remaining 25% to component 2. What do we mean by counting fraction of them to different components? Well, you can understand that by looking at the formula we use to update the parameters. So now when we update the parameter for the mean of the first component, we're just going to do this weighted average. So for every xi, instead of setting it totally in component 1 or 1, we calculate what is the probability that it is in component 1, which is gamma I. So gamma I is a number between 0 and 1. And then we're just going to do a weighted average. So this just stands for a number. So the gamma plus, subscript plus, it is a number we sum over this index I from 1 to n. So gamma subscript I will be what is the total sample size for component 1. But of course, the total sample size where when we do the counting, we allow a fraction of them belong to component 1 or 2. And similarly, we can update our standard deviation this way by weighted average. And also, when we update the mean for the second component, again, we do weighted average, but now the weights is 1 minus gamma I, because that is the probability of xi is from the second component. And then similarly for our pi would be gamma plus divided by n. For example, let's look at this case where our two normals are one-dimensional normal are really far away from each other. Then for all the observations here, we can imagine suppose this is component 1, this is component 2. So blue is component 1 and red is component 2. So for observation here, you're going to find out their gamma I will be close to 1. And here their gamma I will be close to 0, meaning 1 minus gamma I will be close to 1. So you can, for this case, if you look at the update for the mu's, which is almost the same as what we did before, we basically divide the data into two groups. Data on the left will be used to update the blue normal, and data on the right will be used to update the red normal. But of course, in a different scenario, if our two normals are quite close to each other, then this kind of fractional updating makes a lot of sense, because for observation here, it's hard to divide it and hard to allocate it to just one component, because the chance of being to either component could be very close. Okay, so So let's just recap on this iterative scheme. We're going to start with some initial guess of the model parameter theta, and then we're going to compute, for every observation, compute what is the probability you are from component 1 or 2 using the current value of theta. And then we update theta using this weighted sums. And then we can go back, then recalculate the probability, and then update those parameters again until the value of theta gets stabilized. And now this algorithm seems very intuitive, is appealing. The question is the value returned by this algorithm indeed is the MLE of theta that maximizes the marginal likelihood? Here I wanted to emphasize the MLE we wanted to obtain is the MLE maximize the density function of X without Z. So this is a marginal likelihood. And next, I'm going to explain the algorithm, which is the two steps, A and B, are basically the EM algorithm. So we're going to give a general form of EM algorithm and show that indeed this iterative updating scheme will sequentially maximize the marginal likelihood.